Hi, Chem 212 students, and welcome back for our second lecture of week 2. This one is regarding resonance. And so in the last lecture, we reviewed how to draw organic structures as bond line structures. And we also went through how to determine what the number of lone pairs would be on an atom and how to assign formal charges and relate the number of lone pairs given the formal charge of an atom. So you may remember from general chemistry that there is a concept called resonance, and that is that concept that a double bond, the electrons in a double bond may be delocalized and may be able to move around in an extended area. For example, in this what's called an allyl carbocation. So there's a carbon with a positive formal charge known as a carbocation. And this structure is not the only way to represent this particular molecule. So if we look at this, let's think about here what is actually going on in terms of valence bond theory. And so in valence bond theory, the pi bond or double bond is created by the sideways overlap of p orbitals that are unhybridized. And so if we look at each of these carbons and we fill in the hydrogens here, so this has 2 hydrogens, this one, because it's making 2 bonds, this one is making 3 bonds, and so it needs 1 more bond, it has 1 hydrogen. And then for this one, it's a carbocation, which means it's 3 bonds and no lone pairs. And so that means there are 2 hydrogens attached here. And so in this structure, each of these carbons, let's see here. So we have this carbon here in the middle, which has 3 bonded atoms, not number of bonds, but 3 atoms bonded, 1 carbon and 2 hydrogen, and no lone pairs. So that results in a steric number of 3, meaning it's sp2 hybridized. The same is true for this carbon, 3 bonded atoms, no lone pairs, sp2 hybridized. This carbon, 3 bonded atoms, no lone pairs, it is sp2 hybridized. And so all of these have a free p orbital that can participate in this sideways overlap. And the result is that the electrons become delocalized. They can travel between all 3 of the lobes of these p orbitals. And so these 3 p orbitals have a continuous overlap, these unhybridized p orbitals. And again, the results is that the electrons can move all the way through these, and there's going to be 2 electrons, and they're going to be moving between all 3 of these p orbitals. And that's referred to as resonance. When you have these overlapping p orbitals that are like an electron highway, the electron can move freely between them. We can also look at this from a molecular orbital perspective. When we have 3 unhybridized p orbitals, there are 3 molecular orbitals that form their bonding orbital, so-called non-bonding orbital, and an anti-bonding orbital. And going back to our structure here, we have 2 electrons in the p orbitals, the ones involved in this pi bond right here. But those 2 electrons can travel freely between all these lobes, these 3 lobes. But since there are 2 electrons, the 2 electrons are going to occupy the bonding molecular orbital, leading to a stable double bond, a stable pi bond. So which MO is missing? Is the electron missing from? Well, if there were a 3rd electron, it would be in a non-bonding orbital. And the positive charge is spread out throughout the entire molecule. It's not in any one particular place. And so what we can do is we can actually use 2 resonance structures to exhibit the way the electrons move through the atom here. And so if and so here, for example, we're showing the 2 electrons in the p orbitals going through basically on this side of the molecule. And in this resonance structure, we're showing the 2 electrons being on this side. But in reality, they're going across both sides and traveling through the p orbitals. So both resonance structures contribute, and they both are equal. Neither one is accurate. And so the way we demonstrate this, or we write it down on a piece of paper, is we put arrows between the resonance structures and we put brackets around the collection of the resonance structures. And we're saying that neither this is the one on the left is not right, the one on the right is not right. The real structure is in between. So another way to write this is as a so-called resonance hybrid, and that is where we take the 2 double bonds and instead make them 1.5 bonds. So that's the real situation that's going on here is it's like a 1.5 bond between 2 carbon atoms and a 1.5 bond between the other 2. And we get this kind of dash bond representing a half a bond on each side. So how is resonance different from equilibrium? Equilibrium is telling you that a species is interconverting between products and reactants. Products are being formed and then products are going back and forming reactants again. This does not mean that. What this double arrow means is that it is equivalently both at the same time. So resonance results in a more stable molecule. The electrons, when they are spread out, they're easier for each individual, basically for the molecule as a whole to hang on to. And so the electrons, when they're repelled by another electron close by, they can move around. And since the electrons spend time close to multiple nuclei at once, it maximizes the strength of holding on to those electrons. And so we call this a delocalization of charge, and we call it stabilization via delocalization. So the delocalization results in a stabilization of the ion or molecule that is being discussed. So yeah. So the positions of these formal charges and where the electrons are moving around and where resonance structures exist is going to be really important. When we know that there are resonance structures, we know that that will stabilize a particular ion. And so we'll want to know what is going on with that resonance. And so we depict these resonance structures and the so-called interconversion between them. Again, they are really, both resonance structures existing at the same time. But in order to keep track of where resonance structures exist and where they do not, we will use a series of curved arrows here to represent where the electrons are moving around at. And so the arrow will start where the electrons are, and it will end where the electrons are going to end up. And so this curved electron type of notation is going to become extremely important throughout the class. And so this chapter is going to be crucial, and this lecture in particular is going to be crucial for understanding how to deal with these. And so, for example, in this case, there will be another resonance structure that exists. This this pair of electrons has moved. I mean, really, again, it's not moving. They're always moving, and they're free to move between each spot. But we have a double bond now here, and now the formal charge of +1 is over here. Why? Well, because this carbon was initially bonded to 2 hydrogens, and it had a double bond, so it had 4 bonds. But once the electrons have moved, now this carbon has 4 bonds. It had a hydrogen right here because it had 3 bonds and no lone pairs, so it had 1 hydrogen. But now this carbon has, I'll just draw in the hydrogens, has 3 bonds and no lone pairs. So it's the one that has a positive charge. And so that's the other resonance structure that exists here. So if we're going to draw these curved arrows, we have to make sure that they represent things that are actually happening with the electron movement. For example, you would never draw a arrow in a resonance structure, at least. Later on we'll draw it, but for resonance structures, these do not involve the breaking or formation of bonds. And so we would never draw in a resonance structure the arrow starting with a single bond like this, because that would break the bond. And so that's the first rule of using curved arrows to show resonance, is that we're not going to be breaking bonds here. And so the end of the arrow will never start from a single bond. The other one is to never exceed an octet. So these atoms, at least for these atoms here, boron, carbon, nitrogen, oxygen, fluorine, all of those on the second row of the periodic table. The reason is they simply, larger atoms can exceed an octet. Sulfur does it, phosphorus does it. But these small atoms with only energy level 2, there's just not enough room in the atom to make those bonds. That's a gross oversimplification. A real explanation would require quantum mechanics, but just very simply, these atoms are too small to exceed an octet, to fit more than 8 around them. They've got nowhere to put the electrons. So atoms in the second row will never exceed an octet. So you never want to draw a arrow that results in an atom exceeding an octet. For example, the one on the left here, we can't draw an arrow from this lone pair and make it a double bond, because at that point carbon would have 5 bonds, and it would be exceeding an octet with 10 electrons around it. And so, and just I want to emphasize too, in our last lecture we were doing formal charge counting, where we split up bonds and gave 1 electron in the bond to one atom and 1 electron to the other. We only do that to count formal charges. As I said, it's a kind of record keeping or bookkeeping of electrons. It's not real per se. But exceeding an octet is real, meaning when we count an octet, we count all the electrons around the atom. So this carbon has 2, 4, 6, 8 right now. If it has 2 more, that's 10. It's too many. This nitrogen, same thing. It has 2, 4, 6, and 8. It already has 8. Making a double bond here will give it 10. That's not okay. All right. Same for this oxygen. It already has 2, 4, 6, 8. You can't exceed an octet there. Okay. How about this arrow here? This arrow, again, it's an issue. Why? Well, because there's 2 hydrogens here that haven't been drawn in. This carbon already has 4 bonds. If you move this, make this double bond here, you will exceed an octet. So that's not okay. We can't do that. So for second row elements, they will sometimes have less than an octet. So we've already seen an example of the carbocation. And so what we have here is, as opposed to this one, which was not allowed because it would exceed an octet for carbon, this move here of electrons is allowed, and this does represent a valid resonance structure. What we can see here is that 2 of the electrons in the double bond are now becoming a lone pair on the oxygen atom. Okay, and so the result is that this carbon, though, has 3 bonds and no lone pairs. So now we have to indicate formal charges. This oxygen has 3 lone pairs and 1 bond, so it has a negative formal charge. This carbon now has 3 bonds and no lone pairs. It has a positive formal charge. And so the resonance hybrid would be, right in between these two. So it would both have the lone pair on the oxygen and a single bond, but also be a double bond. So this bond is like a 1.5 bond in a sense, particularly because oxygen pulls electrons in towards itself. It's probably a lot closer to a double bond though, but it does have a little bit less of double bond character because there is a resonance structure where the electrons can go up to the oxygen. Is it favorable? No, it's less favorable because it has formal charges. This one on the left would be the more favorable structure. So it would lean more towards this one, but have a little bit of this as well. So when you're using these curved arrows, you're often going to end up with a formal charge. So you have to make sure that you show the formal charge and that all of the rules regarding octets and not breaking bonds are followed. So in this case here, we've got a oxygen here. We've got a couple of movements of electrons. So first of all, the electrons in this double bond are now becoming a lone pair on this carbon atom. And this is allowed because remember, this carbon atom only has one hydrogen attached. And so when it loses this double bond, it still only has 3 bonds and 1 lone pair. So it has not exceeded an octet. However, it does now have a negative formal charge. So I should indicate the negative formal charge for this carbon. Now, the lone pair on this oxygen became a double bond. So there's a double bond here, and now this oxygen only has a single lone pair. Again, this is still allowed. The oxygen has not exceeded an octet. It has 2, 4, 6, 8 around it. However, it does have a formal charge. It's got, if we're counting dots, so notice how the dots for formal charge are different than octet. When we count octet, we count all the electrons in the bond. So 2, 4, 6, 8. When we're doing dots for Lewis structures, what we do is we just split each bond in half and give a dot to each atom. So this oxygen has these 3 blue dots and then the lone pair right here too. So in its little circle right here, it has 5 dots. That is 1 less than its normal 6 valence electrons. So it has a formal charge that is +1 because it has 1 less than its normal 6. So all of this is allowed. The octet rules aren't violated, no bonds are broken, but it results in a structure with formal charge, which is usually less stable. And so there's the results right there written. So what you can do is, for the arrows, they're not real, really the electrons are moving freely back and forth between these resonance structures to some extent, favoring the more stable structure. But these electrons do help us to show where the charge is flowing, or at least help us to understand that in a way that makes sense for us and is easy to analyze. So there's going to be 5 main bonding patterns that you're going to see related to resonance here. And those bonding patterns go like this. Allylic lone pairs, and we'll talk about what allylic means in a moment. Allylic positive charge, it's essentially 1 away from the double bond, is allylic. Lone pairs of electrons adjacent to a positive charge, meaning they can go there because it's lacking electrons, so it's not going to exceed an octet usually. A pi bond between 2 atoms with different electronegativities. We saw that example earlier where oxygen, the electrons in the double bond were pulled towards the oxygen. And conjugated pi bonds in a ring. Conjugated meaning alternating double, single, double, single, double, single. So let's look at a few examples. First of all, let's define these words, vinyl and allyl. So the vinyl position is referring to the atom that is actually involved in the double bond, and something directly attached to that atom. So the vinyl position is the carbon in the double bond. Something attached directly to that carbon is said to be vinyl. Allyl refers to a carbon that is 1 away from the double bond. So something that is attached to the carbon or atom 1 away from the double bond is referred to as vinyl. So you might have heard of PVC, which is polyvinyl chloride. Polyvinyl chloride, right? Which involves a lot of vinyl chlorides. And the reaction of many vinyl chlorides. This is a molecule, the vinyl chloride. So I'm gonna circle the vinyl positions in red. So those are chlorines attached right to the double bond. That includes this chlorine, that includes this chlorine. And I'm going to circle the allyl positions in blue. So allyl positions in blue. This is an allyl chlorine. It is one away from the double bond. It's actually allyl twice. It's allyl to this double bond and allyl to this one. This chlorine is neither allyl nor vinyl, because one away from the, oh no, it is, sorry, it is allyl. So this chlorine is allyl, sorry, because this carbon is one carbon away from the double bond. But this chlorine on the right is neither allyl nor vinyl, because the vinyl position would be right here, one carbon away from the double bond, but this is 2 carbons away. So that's what a vinyl and allyl mean. So what we want to do when we're looking for resonance structures is we're going to try to find allyl lone pairs. And these will be involved in resonance. And so we have, where are the allyl lone pairs? Let's first identify the allyl lone pairs here. So this is an allyl lone pair right here. It's a lone pair that is on a carbon one away from the double bond. These are allyl lone pairs. These are lone pairs on an oxygen the allyl lone pairs. Actually, these are vinyl lone pair. A vinyl lone pair there. On the oxygen. So here we have an allyl. So here's a few examples. Allyl lone pair. All right. And so let's now draw arrows on these structures to show the resonance for them. And so we'll do this on this next slide here. So here, remember this carbon here has 2 hydrogens. Okay. And the result is going to be, when we have allyl lone pairs like this, they can make a double bond next to themselves in this way. And then the double bond, its electrons will go on the neighboring carbon. So this carbon, notice that now it's going to have a lone pair. So I'll just draw that carbon. So we got a carbon right there. It's going to have a single bond. It's got 2 hydrogens attached. I can draw the hydrogens if it helps here. And so this is a carbon with 3 bonds and 1 lone pair. It is now got the negative formal charge. And now this one right here is the double bond. And so that's our resonance structure there. Okay. And so now we've got this allyl lone pair right here. Okay, so it's on the oxygen that's next to the carbon that has the double bond. And so it is an allyl a lone pair. Both of these are. We just choose one. We do the same thing here. This lone pair turns to a double bond, and then on this double bond, it becomes a lone pair on the carbon. So the situation is similar to the left. I drew it in a little bit more detail there. But this is a carbon with a lone pair, so it has a negative formal charge, 3 bonds, 1 lone pair. And then we have a double bond here. Oxygen has a single lone pair left and one more bond. So this oxygen is making 3 bonds and has 1 lone pair. So that gives it a positive formal charge. And normally it would make 2 bonds and 2 lone pairs, so it's lacking 1 electron. Okay, so that's our resonance for that. Here we have another situation with an allyl lone pair. So this one will make a double bond, and then this one will make a lone pair to that oxygen, And so we have now this oxygen with 3 lone pairs and 1 bond. That is a oxygen with a -1 formal charge. And then this oxygen here has a lone pair and a double bond here, a single bond here. So 3 bonds, 1 lone pair. That is an oxygen with a positive formal charge. Here we have another allyl lone pair, and so it's on the carbon 1 away from the double bond, and so we have the same pattern. Makes a double bond to that carbon that was in the double bond, and then the double bond ends up leaving a lone pair on the atom that's on the other side of the double bond. All right, so we got a double bond here. This nitrogen now has 1 lone pair. Actually, let's see, it started with 2 lone pairs actually, or 1 lone pair already. It wasn't written. So now it has 2 lone pairs. So now we can see that this is a nitrogen with 2 lone pairs and 2 bonds. It has 1 more electron than it should have. 6 dots, if we count a dot here, and then 4 dots here, that's 6, compared to nitrogen usually being a 5 valence electron atom. So now with this carbon, it had 3 bonds and 1 lone pair. There was a hydrogen here, not shown. And so that hydrogen is still there. So now the carbon's making 4 bonds. It has no formal charge to it anymore. And then finally, one more. This is another allyl lone pair here. And so we have the oxygen. It now has 6 valence electrons. 6 electrons in lone pairs. And I made the double bond by accident. I need to fix that. Should be single bond now. So it's single bond because these electrons in the double bond went up as a lone pair in the oxygen. This is a double bond to this nitrogen, which no longer has a lone pair. Now it's making 4 bonds with no lone pairs. And so that is a positive formal charge for the nitrogen. This oxygen has 3 lone pairs and 1 bond. That is a negative formal charge for the oxygen. Whoops, I was in the way a little bit there. There's the structure. Okay. So you just saw a few examples of how to deal with the allyl formal charge. Again, the allyl lone pair. We make the lone pair into a double bond on the carbon neighboring the double bond, and then the electrons in the double bond go on and leave a lone pair on the carbon that is opposite on the double bond, or other atom. It could be an oxygen. Now, this is also possible with allylic positive formal charge. And why is this similar with allylic positive formal charge? Well, it's because for a carbon like this, for example, it has 3 bonds and no lone pairs. That's why it has the allylic formal charge, or the positive formal charge. But that means that it's open to another bond, and so we can make a bond right there. And now this carbon would now have 4 bonds. It still has its 2 hydrogens, but now it has a double bond to this carbon. However, this carbon had 1 hydrogen attached. So now it has these 2 bonds and it still has this 1 hydrogen. This means that it's making 3 bonds with no lone pairs. That is a positive formal charge on that carbon. And this could happen again. It can go again right here, and we can do it one more time. So there's actually 3 resonance hybrids here. So far we've got 2. Just going back, we've got allylic lone pair, we've got allylic positive charge. The other situation is a lone pair adjacent to a positive charge. So for this one, did you notice when we did allylic lone pair, we needed 2 arrows, but when we did allylic positive formal charge, we only needed 1. That's also true in this case. So for case number 3, a lone pair adjacent to a positive charge, we only need 1 arrow. And so we can see here in this example, the oxygen has a negative formal charge because it has 3 lone pairs and 1 bond. Then that lone pair, the electrons move down and become a double bond. Now that was okay because this carbon was making 3 bonds with no lone pairs. We know because it had the positive formal charge. And so now it's making 4 bonds. So this carbon is making 4 bonds, no lone pairs. It's got 0 formal charge. And this oxygen is making 2 bonds, 2 lone pairs. It's got 0 formal charge. Okay. And here we have another one where we have a lone pair adjacent to an atom with a positive formal charge. Again, this carbon's only making 3 bonds with no lone pairs right now. It doesn't have an octet. That's why it has the positive charge. And so this lone pair can make a double bond. Now this carbon here is making 4 bonds with no lone pairs. There's a hydrogen here. There was here. There was a hydrogen attached. It's not shown, but the hydrogen is still there. It's right there. And the oxygen, though, now is making 3 bonds with 1 lone pair, so it has a positive formal charge to it. Here's another example of a lone pair adjacent to a positive charge. And so here, the one issue is that this actually is not going to work. Not in one step anyway, not with 1 arrow. So there are situations where you could have to use more than 1 arrow. And this is one of those situations because let's say we make the double bond here. Now this nitrogen has exceeded an octet because it already had an octet, but we can fix that with 2 steps. So what we're going to do is we're going to now say these electrons here moved over here. So the other resonance contributor would be a double bond to this oxygen with 2 lone pairs and a single bond to this oxygen with 3 lone pairs. And now this oxygen would have the negative formal charge to it. So the one where we just make 1 arrow and leave it, that can't be a resonance contributor because the nitrogen would exceed its octet. The fourth situation where we could have resonance is if we have a pi bond between 2 atoms of differing electronegativity. And so this, going back to this, that results in one more possible resonance structure. I just want to go back to this one because we hadn't really talked about it yet, but we could have done, now that we have this 4th rule, is we could have said, okay, we're going to do the first step where this oxygen, because that's following this rule here, a pi bond between atoms of differing electronegativity. Oxygen has higher electronegativity than nitrogen. So the result would be that the nitrogen would have a positive 2 formal charge, and the oxygen now here would have a negative 1 formal charge, and this one would have a negative 1 formal charge. Now this is a highly unstable situation, so this would quickly be resolved when this lone pair that is adjacent to a positive formal charge then goes and makes the double bond, and at that point we'd be back at this resonance structure that we drew last right here. So that would be all of the resonance structures together. So here's another example of that. We've seen this one going the opposite direction before. So we've gone in the opposite direction from lone pair adjacent to a positive formal charge, and we went and made this structure on the left. We can also do the opposite. Since oxygen has a much greater electronegativity than carbon, we can simply move these electrons over here. So just this red arrow you see there, I'll just kind of highlight on it like that. And the result is that after that, this oxygen has 1 bond and 3 lone pairs. It is got a negative formal charge, -1, and this carbon has 3 bonds and no lone pairs. So it has a +1 formal charge. So we can do a similar thing right here. This nitrogen is more electronegative than the carbon, and it's a part of the pi bond. So we can move that to make it a lone pair. We can move that set of electrons in the pi bond to make it a lone pair. So that gives this nitrogen 2 lone pairs, and it still has that bond out there. But now it has 2 bonds and 2 lone pairs. So the nitrogen has a -1 formal charge, and this carbon has 3 bonds and no lone pairs. So it has a +1 formal charge. Finally, conjugate pi bonds in a ring. This is going to become very important in a certain chapter later on in Chem 203 especially. And what happens here is that these electrons are delocalized around the entire ring here, because the electrons can essentially move here. We got the pi electrons. There's basically 1 pi electron excuse me, in each of these sp2 hybridized carbons. So you can see that each of these is making 3 bonds, so each would have a hydrogen. So we have 3 atoms bonded and no lone pairs. So that results in a steric number of 3, which means sp2 hybridization for each of these carbons here. They're on the double bond. And so the result is that the electrons can travel through all these p orbitals all the way around. And so we represent this by drawing lines, curved lines, which represent the movement of each double bond by 1 spot. And that's what you see here. And you can do it in either direction. It does not matter, clockwise or counterclockwise. What type of motion do the electrons actually have? Well, they move in very mysterious ways, dictated by quantum mechanics. They jump around a lot, but they jump around within this ring, and so they're delocalized. They're just spread out all over this ring here. So to summarize, you're going to be looking for one of these 5 patterns to know whether resonance applies to your molecule and how to show the resonance structures. An allylic lone pair, a lone pair situated on an atom that's attached to the carbon involved in a double bond, or another atom, or an atom involved in the double bond. This requires 2 curved arrows every time. You can have an allylic positive formal charge, a positive formal charge on the carbon attached to the carbon in the double bond or other atom. A positive formal charge adjacent to a lone pair, 1 curved arrow for that one as well. A pi bond between 2 atoms of differing electronegativity, that's 1 arrow here. And conjugated pi bonds in a ring. This depends on the size of the ring. In this ring, it's 3 double bonds, so there's 3 curved arrows. So let's take a look at this molecule. So when molecules get big, analyzing all the possible resonance contributions can be, can be tricky. It takes a little bit of practice, and so that's what a lot of the homework for this week is about. So let's try to look at some of the patterns that we see in here. So first of all, we have a positive formal charge adjacent to a lone pair. So for this situation here, we've got that going on right there. Okay. We've got an allylic lone pair as well. So we've got an allylic lone pair. That is what's going on right here. This oxygen is allylic to this there's the lone pairs on this oxygen are allylic to this double bond here. So lone pairs right here allylic to this double bond. An important note is that this positive charge is also allylic. So we have a situation of this. So this positive charge right here is allylic as well. It's allylic to this double bond right here, further down. And finally, we have also a pi bond that is between two atoms of differing electronegativity that's going on right here. And so there's lots and lots of possible resonance contributors here. There's tons of them. And so let's take a look at what we could do. I'm going to erase what I wrote already, just to clear up some room. So let's start with the lone, let's see, let's start with this. We'll start at the bottom right where the oxygen is. And so we have a lone pair allylic to a double bond. So this goes right here, and then this goes right here. And so what we have is okay, and then we have a carbanion here, which is single bond, and then we have a double bond to this oxygen. Okay. This wasn't drawn in the best way, the carbanion. So there's a lone pair here on a carbon with 3 bonds, so it has a negative formal charge. This one has a positive formal charge. So now what we have is we have a lone pair adjacent to a positive charge. So we can now do an arrow. I'm going to do a blue arrow for this lone pair to make a double bond there. And so that would give us a structure where we have so this is single, and then this would be a double bond here, and this nitrogen still has a lone pair, and then we have, there we go. Okay. And then we still have the oxygen here. All right, and now we have a we also have the lone pair here on the nitrogen, allylic to the double bond. So I'm just going to show the kind of last few. I won't draw them out, but the last few possibilities here are we have a lone pair allylic to a double bond. So we could go like that, make a double bond there, and then that would leave again the carbanion over here. So that would be another possibility. What about this right here, the nitrogen? That's another possibility as well, because that has that's this situation here, pi bond between two atoms of differing electronegativity. So also we could have electrons move there. And so the result there would be a negative formal charge on the nitrogen and a positive formal charge on the carbon. So there are lots and lots of resonance contributors for this particular structure. And so you're going to get some more practice with that on the homework. I will do this one. I have some room on the left. So what I'm going to do is I'm going to erase the arrows that I put at first. And I'm going to just do this one right here. So if we were just doing this one, there's so many possibilities. It would take a long time to write them all. But this is a lone pair allylic to, a pi bond between two atoms of differing electronegativity. And so if we drew that structure, it would be a nitrogen with two lone pairs and 2 bonds, which is a negative formal charge on the nitrogen. This carbon here would end up with 3 bonds and no lone pairs, so it would have a positive formal charge. And then I'll just write the rest like it was. Okay. And so again, yeah, lots and lots of possible structures here. One thing, if you're having trouble with the formal charges, make sure to write out your hydrogens and keep in mind how many bonds each carbon is actually making. Also, one note is that if you take a look, you'll notice that whenever a resonance situation happens, the total addition of all the formal charges stays the same. So here we have 1 positive formal charge and 1 negative formal charge for a net charge of 0. That's also true in our structure here, a negative and a positive, a net charge of 0. The structure over on the right had no formal charges, so a net charge of 0. Here there's 2 positive on the left, there's 2 positive formal charges and 2 negatives. Again, a net charge of 0. So one way you can spot that you've made a mistake is that if your formal charges are not, when you add them all together, aren't the same as what they were when you started, it means you missed something somewhere. You're going to want to try again. Finally, the relative stability of contributors to the structure. I think this is going to take a little bit of time, and this video is already about 45 minutes, so I'm going to stop here and we'll finish the last couple of sections in the chapter on the next video. I'll see you in the next one.